So I'm going to start now, share my screen first of all, and then I'm just going to get you into the NMR box. I assume a lot of you are box users already, but maybe not everybody. So let's start by sharing my desktop. So you should see now my desktop. I'm running on Mac here. I have already installed the Vnc Viewer program. And I should say, if you go back to the recordings of the previous workshop, you can probably see a video walking through how to do all this stuff. So we'll go kind of quickly here. So I'm going to start up Vnc Viewer. You'll get this little interface where you can connect, and basically, I'm going to do it a little bit different, but I'll show you what you can do. You can type in, and the box people can scream at me if I'm doing this wrong, but you can type in your username.nmrbox.org and hit a return, and that will take you to a virtual machine. There are a whole series of virtual machines running at NMRBox, so lots of hardware out there. It's possible to pre-populate a list downloaded from NMRBox of all the machines, and you can actually go onto the NMRBox webpage after you're logged in and see which ones are more or less used and select one you want. I'm actually going to go to this phosphorus one, which I have pre-configured already with some stuff running on it. So I'm just going to double click here, but if you were just typing in up there, you just hit a return and off you will go. If you haven't logged into that machine before and saved a password, you'll get a prompt which will ask you for your username and password. Once you get in though, you will see a desktop. Your desktop will be empty and it will probably be smaller than mine. So one of the first things that I do when I go to a new VM is I go up, and let me actually, let's pause for a second here and give people a chance to have logged in. If you're having trouble with that, don't hesitate to pop up and ask for help. Once I'm in there, you can click up here on this icon, and there is installed a program called Resolution Changer. If you bring that up, you'll see a whole series of resolutions that you can choose from. And the default one is rather small. So depending on what sort of desktop size you have, you can choose another size and just click and it will resize. I'm going to say, no, I don't want that one. I'm going to go back to 1920 by 1080 and apply and keep and confirm. So that should have resized your VM. Now, just to be a little more space efficient of screen, I'm going to stop my sharing and actually have Zoom share just this Vnc Viewer window. So I'm going to do stop share, and then I'm going to go back and I'm going to share screen again. And this time I'm going to choose just the Vnc Viewer. So now you should see my viewer. I'm going to give you about a 1-minute historical background here. So if you're still having trouble popping in, don't hesitate to chime in, ask for help while I'm doing that. Okay, so I put a little historical thing here that's going to sort of rationalize what we've been trying to do over the last few years. Things are getting more and more interesting techniques for people to use these days, not just NMR, cryo-EM, X-ray, etc. People, when they come to NMR, they tend to be a little bit overwhelmed with the number of different software packages they are, and nmrbox is simultaneously a testament, a great advance in this, because it actually pre-installs and packages up a lot of these different packages for you, so you don't have to do it yourself. But it's also a testament that there's so many choices of programs to run, etc., that can be a little bit overwhelming. So we had the idea of coming up with what I sometimes refer to as sort of soup to nuts one sort of integrated package to get you from raw NMR data to a structure or titration analysis, etc. And it seemed a little bit crazy to do this, but then I looked back over the years, and going way back into the 80s, we started developing software for NMR, signal processing, molecular structure visualization, MSurf. Pegasus was a protein structure calculation program. A lot of these none of you have ever heard of those. The one that really took off and did it well with thousands of citations now is nmrbox20, which we first started releasing back in the early 1990s. So I don't even like to do the math and figure out how many years that's been going on. It was basically visualization. So once you'd processed, way back then, we would process an FTNMR or Felix. More recently, a program like NMR Pipe. Once you've done your processing, you could go in nmrbox20 and do all the visualization, peak picking, assignments, and things like that. I spun off a couple programs from that, a Datacord, a small molecule analysis program, and Datacord Spectrum Miner for metabonomics, both of which are actually in the box. And those started incorporating some processing, and it struck me that we might be able to actually fill in the whole, as I say, soup to nuts. So we developed, starting about 4 or 5 years ago, nmrfx processor for processing NMR data. And we sort of have an evolution of this Pegasus program for structure calculation. So that's led to, if I pop over different icon, to this nmrfx integrated software for NMR analysis. It's all pre-installed in the NMR box, but you can also go directly to nmrfx.org and download. You can run executables on Linux, on Windows, on Mac, on your local computer, or in the box. You'll see here several programs listed. Processor was our first version of processing. There's really no point in downloading it because everything in the processor is integrated in this analyst. nmrbox20 still exists as visualization analysis, but what we're doing is gradually moving the features, and I'll show you some of those that are there already in the analyst, and some will give you some highlights of works in progress that are coming along. So at the moment, there are still analysis things that you still would want nmrbox20 for, but we're gradually putting all those into analyst. And then the structure calculation program is a fine one. So if you actually want, downloadable versions for your own laptop, etc., you can go there. But we're going to do everything today in the box. I'll mention that everything now, for years, it kind of hid all the software. Everything is now open source. You go to GitHub, OneMoonSci, even though it's still under the name of my small company, it is all open source. So you can find the source code for any of these. And if you find bugs, you can go in, for example, go to the issues and add a new issue to report on a problem that you find. Don't believe that there aren't any open issues. There are problems that we actually maintain inside at the Advanced Science Research Center at City University of New York, where I sit up in Harlem when there's not a COVID pandemic going on. We have our own tracking GitLab system there, but we sync that periodically to the external GitHub site. So I'm now going to start running things. I haven't heard anybody having any troubles. So like I say, you can, if you're in the box, you can follow along with everything I do. We'll periodically pause and let you catch up. Don't hesitate to chime in if you have any troubles. So let's just try that. So first thing I would do, once you're in the box and have a nice open screen there, we could click on a terminal emulator, terminal program, and we'll have a Linux shell here. It's possible to start nmrfx. I think from these icons up here today, we'll do everything from the command line. There are several programs. I'm going to walk you through a little bit what they are. In your folder, if you do an ls, you should find this summer workshop 2020. That should have been migrated into your folder. So I'm going to CD into there, and in there, there's Johnson. As the summer goes on and more of these workshops happen, those will fill up with more examples. So I've put a bunch of example data in here that we'll work with today. Just real quickly, I'm going to go into this scripts directory, which I just copied in today. So hopefully it migrated everybody. Not important if you don't have it. To run the software, there are several ways. To start the full analyst GUI program, there's this long nmrfx analyst you can run. There are also some shortcuts if you don't like to type so many letters. If I hit nmrfx and hit a tab, you can see that there are 3 programs installed. nmrfx is the full GUI program. That's the same thing as if you typed up the full nmrfx analyst. Although somewhat strangely, if you run it as the full nmrfx analyst, it will tell you in the top of each screen what version you're running, which can be useful. From this little shortcut, it doesn't show you that. That's something we'll fix soon. So nmrfx is the full GUI. nmrfx-A is a command line version, and it can do things like processing. So if I just type nmrfx-A process.py, this for pipe users would work very much like pipe, where you would just type a command and hit a processing script. In our case, processing scripts are written in Python. So that ran, it will have created in our folder this hsqc.nv file. And I can see that if I use the GUI version, nmrfx hsqc.nv. That'll pop up. So boom, we did a quick process of an HSQC. We'll come back and look at this more later. So that's nmrfx, the GUI version, nmrfx-A, the analyst version to run scripts in command line, and nmrfx-S is a structure calculation. I can just type nmrfx-S gen project.yaml. We may or may not get to some of these things we may not get to today, and so I'm just giving you a quick overview of these things exist. So there we've done, we're doing a quick structure, torsion angle molecular dynamics on a small RNA with just some constraints that set up helix. And so that's run, and I can do pymol output. It will put one file in the output directory, and boom, there we folded up and made a nice little stem turn RNA. So those are the 3 programs that you may use for doing this. nmrfx, the GUI program, A, the command line processing program, and S, the structure calculation program, which does a variety of other things like chemical shift prediction, etc. So let's start up nmrfx, the GUI version, and let's start thinking about processing data. So when you start it up, you're going to get one window here, spectrum window. I'm going to walk you through processing a little bit step by step. For some of this will be, seem like, real basic tutorial stuff, but by doing the step-by-step stuff, I can show you a little bit about how the interface works, and also we'll talk a little bit about some stuff involved in NMR processing for those that are new to it. Normally, we would open up a raw data set from the file menu, but I'm going to go to the view menu and show processor. And that gives us this little control window here where we can set up processing operations. There are several tabs here. Parameters we'll use later for actually dealing with our actual data set referencing. Operations is the single most important part here. It's a list of processing operations. Again, for NMR pipe users, it will be very familiar in that in pipe script, you have a list of commands to do, sine, Bell aptization, Fourier Transform, etc. Here, we're going to do that, build up a list in a similar way. to get you used to using the interface, I'm going to do this actually on just simulate some data. And one thing we've tried to do is to make the program useful for educational use. And I periodically see bursts of downloads from groups that are courses where they're using it to teach classes. So we tried to make this kind of educational. So this little menu arrow here is a menu, and from it we can choose any of the processing operations. Because we're going to do a little simulation here, we start with things in the simulate submenu. And this first one, vecref, you can think of as basically choosing the spectrometer we're going to work on. So we can set the size of data we are collecting, the spectrometer frequency defaulting to 500, the sweep width, basically. We don't see any data yet. That just sets up these parameters for what the simulation will use. Let's go to next thing. Let's try simulate gen. So generate an FID. Let's pop over here. We'll start learning about some of the controls up here. Auto scale, auto scales, and we can go up and down. Every time you insert a processing operation, almost every processing operation has a variety of parameters that determine how it's used. So one reason for showing you this, walking through this, is to show how we use these parameters. So for example, to generate an FID, you can set the frequency. So I can just slide an FID, the slider here, and it changes the frequency. Every parameter, every operation has a default. If you're actually at the default, you won't see a parameter here, but as soon as you start sliding, so for example, the line width defaults to 1 hertz, but if I start sliding this, then it inserts the line width parameter there. So now we've got a frequency of 140 hertz. We can actually, if we want to get exact, we can type values in. We'll come back to these scales here. Basically, you can change the range of the slider to zoom in and zoom out with the plus and minus values over here. We can change the amplitude of the signal like this. As I'm sure you all know, NMR data is generally complex, so we can see the real and the imaginary data points there. It turns out some fundamental facts of the signals of NMR are such that it's essentially almost always a good idea to zero fill your data at least once. We'll come back to how that, why that matters in a little bit. If I go back to vecref, you can see we actually have a size is actually, it's at 8 there, and that's 2 to the 8th. So we have 256 real points and 256 imaginary data points. So we have 512 pieces of information, we can say. So I'm going to zero fill, transform ZF. So now we've got a zero fill of values. Let's go ahead now. This is in the time domain. So let's insert a Fourier transform. FT, I'll turn off the complex values. So we can see that we have some artifacts in the spectrum. If we're actually doing this live in an audience, I would reach out to you guys and have people tell me why that is. Every operation, and kind of a nice feature, I think, can be disabled. So if I want to see the effect of this operation, I can turn it on and off. Somehow in the box here, I get these. I need to re-auto scale to get that going. So those wiggles come when we zero filled. We actually have this sharp transition from signal, which decays away immediately 0, and that gives rise to these sync wiggles, which is why we almost always insert an appization. So under appization, we have a whole series of functions. Let's go back to just the FID so we can see the appization work. The ones that you're probably most familiar with are exponential decay and sine bell, but we give you a variety of other things. There are some reason that the Kaiser window is considered, some reasons it's considered an optimal value in terms of its ability to suppress those sync wiggles without losing much intensity. Probably the most common one to use is sine bell, so let's go back to that. Any operation, we can just highlight and hit the delete key, and it's gone. So let's go down, sine bell, insert appization. Apodization, this is a sine bell squared window by default. We can shift the offset and convert it into a cosine window. We can change the power here, change it from sine bell squared to just sine bell. And let's go back to our FT and disable. Okay, so there, now because we've apodized the signal, we've essentially forced the intensity to go to 0. We don't have a sharp transition anymore, and we've lost those sync windows. What's become very popular, and I'm sure there was quite a bit of talk about it at the first workshop, and in a few weeks you'll hear about, I think, SMILE processing for NUS processing. You hear quite a bit about NUS processing. So let's look at that real quickly. We can come to an operation under sampling, and we can insert a sampling schedule. We use this just for the purpose of these simulations and testing. This is inserting a Poisson gap. By default, just 5% of the data, and we can play around with that. So basically, you can see it's a little hard because we have a continuous line rather than just dots. So basically, wherever there's zeros, that's unsampled data. Let's see what happens if we go to the Fourier Transform of that data. So let's re-enable our FT. And you can see we have still have our signal, but we have a lot of noise here. I want to convince you of something that's rather important that isn't always obvious when one reads and looks at NUS processing. We often see all this noise out here. If we come back to this schedule, let's actually watch what happens to our signal and to these artifacts as we change the sampling schedule. So I'm going to change the schedule, and note as I increase the % of sampled data up to finally we get to 1 where it's fully sampled, what I want you to watch is to see that center signal is actually falling, and this noise, we'll call it, is actually increasing. So it's not simply a matter that we're adding noise, we're actually losing signal here, and may have been talked about at the last session, the so-called point spread function. What we're actually doing by the sampling schedule, the missing point, is actually spreading data from this core signal, spreading it out into different frequency bins. And so the signal is simultaneously going down where we're adding this noise, and in that sense it's not really noise, it's actually signal that we really wish was here at the central, at the actual frequency of our signal, but is getting displaced out into other parts of the spectrum. However you look at it, that's a problem for us. We've lost signal, and basically the ratio of signal and noise has gotten worse. So that wasn't a great thing to do, introducing that sampling schedule. The reason for doing it is in higher dimensions, we only have to collect a fraction of the data, and we can do our data collection faster in the indirect domain. So we provide several ways to deal with this. It's a huge area of research over the last number of years in terms of algorithms for dealing with this. Let's go back to look at our time domain signal. So we give a few methods for processing this data. So I'll go to sampling. One of the first ones that people were using, Iterative Self-Thresholding, IST. So let's just insert that as an operation. So you can see basically inserting that, we've basically, all those values that were zeroed are essentially now set to what look like correctly sampled values. So what we've done is we have a variety of algorithms that basically can, in some sense, estimate the values that we didn't measure and replace them. So if I go back now to our FT, we have a little bit of residual wiggle here, but basically we recovered our signal by introducing this IST, Iterative Self-Thresholding. There are many different options here. As you might gather from the I, Iterative Self-Thresholding, it's iterative, so we can see actually what happens as we change the number of iterations. So if we only do one iteration, we don't get much. As we increase the number of iterations, which takes, the reason these take time to process is because each of these operations involves a forward and a backwards Fourier transform. So you don't want to do too many iterations, but you want to do enough to actually recover the signal. So you can see for this example, I need to get up around 500 samples. A variety of other parameters that come into play there as well. We can remove that IST operation. We also have nest A. It came out of Andy Bird's group. Nest A stands for the Nesterov algorithm. This is not their code. This is my interpretation of their algorithm. But if we insert that, you can see again, we've recovered. We go back, disable our FT. You can see we recovered the missing data points. We have one other method in here. There's a variety listed in here. Grins, for some reason, small. Just a second. I see a raised hand.
Oh, hey, Bruce.
Yeah.
Rajan here. So the question is, you said that the number of iterations, for example, IST or Nest A, the more number of iterations is going to obviously take more time.
Yes.
But the way you demonstrated, the time domain and reconstructed FID seemed to have happened pretty fast.
Yeah.
So is it reconstructing the FID, the time domain data? First question. Number two, is there some trick that you're doing where it appears almost instantaneous, notwithstanding number of iterations?
Let's go back to back to the IST method, and let's turn off the FT. Don't know why I get this little artifact there. And go back to IST and go down. So yeah. So you can see it does take multiple iterations to get there. The fact that this looks so perfect comes in part because we really are starting with, I have a perfect signal. I didn't add any noise to the signal. It's a single decay, so your real data is going to be trickier, but it does start recovering fairly quickly. I guess the effect in the FID, well, it still takes, still takes quite a few iterations to really 500, so to get pretty good. I'm not sure if I'm actually answering your question or not.
So the point is, both the methods you showed, so the reconstruction is happening in the time domain before the Fourier transform is done, or is it doing the FT in an iterative fashion and looks for improving? I mean, in Frank's the last session thing, the idea was it is able to recognize the peaks, and then using that it improves the prediction and so on.
So the IST method, a lot of these methods are actually working in really in both domains. And that's why when I said when you do 500 iterations, it's 500 forward and 500 backwards Fourier transform. So basically you can imagine back, if I have very few iterations, then I still have a bit of a peak here. So the idea of iterative self-thresholding, and of course we don't have time to go through all the theory of all these, but basically if I put a threshold across the spectrum, if I can get my other, if I put a threshold across the spectrum and I have it high enough to be above the noise, and I basically chop off this little bit of peak, and I copy that into a buffer, I can inverse transform that and put it back and replace the missing data points. And now I have a little bit of intensity in those missing data points. So then next time I transform, the ratio between the signal and the artifacts is higher. And so I can cut my threshold a little bit lower because the artifacts keep getting lower and lower. So I can keep moving my threshold farther and farther down. And so that's basically what's happening as I get, and so then I'm able to encompass signals. I've only got one signal here, but as I lower the threshold, I'm going to include peaks that are of lower intensity.
Right.
And I keep filling in basically those missing data points in the sampled FID so that the artifacts are lower, and I can basically make the threshold go down lower. So that's the necessity of doing multiple iterations in this particular algorithm.
Okay, so it is a forward inverse
Yes.
IFT, FT,
Yes,
back and
exactly.
forth.
And that's basically fundamentally why it takes so long. You know, if you're doing this, it's very quick here in my simple example in 1D, but you're doing exactly the same thing in 2 or 3D.
3D, yeah.
And then you're having to do, if you're doing a 4D experiment, you're having to do, I mean, the indirect dimensions, you know, hundreds of 3D forward and backward transforms.
Oh, great. I mean, that's pretty clear, yeah.
The other one I mentioned, GRINS, basically, it's GRINS is my silly acronym, which recursive acronym. GRINS is not SMILE, so it's sort of it's inspired a little bit by IST and by the SMILE algorithm, which you may have heard from Frank, and you hear again in the later workshop if you watch that. Basically, instead of just chopping off the signal, we're actually doing basically finding peaks and fitting peaks and subtracting off entire peak signals and doing that again iteratively until there aren't any peaks left in the spectrum. Each time we chop off, find a peak, we use the inverse transform of that peak to repopulate our missing time domain data. And that would work here. For some reason, I have a small bug that if I actually insert GRINS in the simulation mode, it seems to throw an error, but we'll use it on real data in a little bit.
Bruce,
okay,
can I add a question? Can
yes.
I add a comment?
Yes.
To Rajan. So Bruce is exactly right. To do any of these processes, you're doing many Fourier transforms. And part of the efficiency of the software, Bruce is very modest here because it's done very well, is how you manage data and how you do these transforms. Michelle Gill, who really finished up and did the lion's share of the work on the Nesta algorithm from our lab, actually went and found sort of non-standard Fourier transform routines, really optimized, and spent a lot of time coding how you manage this data. Because when you get to 3 and 4 dimensions, there's so many FTs. I mean, it's kind of like Amundsen's algorithm of molecular dynamics, right? The number of possibilities and what you got, it just explodes on you tremendously.
Right.
So that's why, you know, with 1D and a small number of points, it's really fast. And the trick is making that really efficient as you go forward. So Bruce is exactly right. And what he's showing you here is really quite well optimized.
Right, okay.
And we've got pretty good performance on, we'll show you on real 3D, running things in a parallel. And a big push for this year is to move us into the world of GPUs, which are really optimized for doing these FTs. So that's one of our goals. So let's just
Bruce,
wrap
sorry,
up.
before you jump into the next topic there, you've got one more person with their hand raised. Alexander?
Yes.
Oh, yeah, that's Alex Lesky. I just noticed about iterations there in the IST. Actually, if you start increasing it beyond 500, it seems like you get more artifacts, right? So,
yeah, that's a good question. And here's one thing that might be going on there is, you know, how do you know, for almost all of these algorithms, there's a huge question of how to know when to stop.
Right.
If you keep going too far, as I said, you basically end up now getting down into the noise, and so that could be one thing that's going on. We don't have in our implementation of IST, we don't have basically a stop detection method that basically says you've gone far enough. It basically, if you say do 1,000 iterations, it does 1,000 iterations, and that's. A, it would be faster if it actually detected when to stop, and B, it looks like, you know, certainly in this simulation, like you could get worse. Now, simulation is a little artifactual because I didn't introduce any actual real noise. And I actually should say we can actually, in Simulate, we can actually add random noise. So now we've added a certain amount of random noise. And so actually doing things sometimes with perfect data, sometimes is actually more artifactual than with real data.
Bruce, if I just add just a couple notes on the theory. All these iterative algorithms are more or less ad hoc approaches to something that minimizes the L1 norm. The fixed point of most of these algorithms is the L1 norm. And it turns out that that actually, if you actually get to the fixed point, you actually introduce a new set of artifacts that have to do with non-random baselines. So, you know, almost somewhat independent from the artifacts that come in from the sampling schedule.
Right.
These L1 norm algorithms, these things that have a fixed point of corresponding to minimum L1 norm, end up introducing non-random baseline artifacts. And I think I've published on that, but I'll dig it out and I can post some references.
That'd be cool. And you know, I'm happy to have these questions because and comments from Jeff, because one of our real goals in this whole nmrfx GUI was to make it easy to actually look at these things and play and to talk about it and have actual, you know, oh, what happens as I change the number of iterations? Like I say, what happens to the signal of the peak, the noise of the peak? What happens to the artifacts? So you really can sort of go in here and play and talk about how this stuff works. So that was one real goal, and I'm happy to see people playing with it and commenting. So let's add one more thing that's relevant in doing a variety of these things. It wasn't talked a lot about in some of the earlier NUS processing stuff, but it's actually pretty important. If I go back to Gen FID, we talked about how the data is complex. I simulated a spectrum or an FID that was perfectly phased, but now let's change the phase of that. So now you see two things. One, the phase of the signal is actually changed, and the artifacts are rather worse. And that's because the algorithm, as I've implemented it in IST, assumes that we have started with perfectly phased data. I'm going to go to let's go to the NestA algorithm. Let's insert that one. Sampling NestA. So we still have some artifacts there. This is the one I actually use more real. So it's actually important that we actually have the operation in the NestA algorithm to tell it what the phasing is, because as I say, we basically go into a mode where the data is all real, and we use a form, the Hilbert transform, to get back our complex data. And so if the data is not properly phased, it's not going to work well. So you can see I can actually insert a phase value into the NestA algorithm itself. So actually, I changed the phase by 62 degrees, and now rather than actually doing a phase adjustment, I've actually inserted a phase correction into the NestA operation. So the first thing it'll do is actually do some phasing. So now you can see that it's phased, and some of the artifacts are gone. I think. Well, let's show real quickly one more little thing. So just to walk through other operations, we can convert our data all real. If I disable that, you can see we had complex data. If I re-enable it, now I've thrown away the real data or the imaginary data. I can insert in here, and I'm only going to show you this just to explain in an empirical way a comment I made earlier. I'm going to insert this HFT, and I should note, every time you insert an operation, add an operation, I've got a list of things where I think it ought to go into the scheme. So generally speaking, when you add an operation, you know, your sign bell is going to pop in before the zero fill, etc. I want this to come after the real, so I'm going to click it, and I can just drag it down. And so now it's after the real. So you can see my complex data has come back. And the point I wanted to make about that was I mentioned earlier that we should always zero fill our data once. And the reason for that is when we get into, it's Jeff can talk to us, I'm sure, for hours explaining why this is much better than I can. But the gist of it is when we get into the frequency domain, the real and the imaginary data points are not independent of each other. I can discard the imaginary data points and I can recover them. So if I started out, I said, with 256 real and 256 imaginary data points, I did the Fourier transform in the end, I would end up with 256 real and imaginary in the frequency domain, but I can get rid of those imaginary. So in that sense, I've kind of lost some signal or lost some information. Zero filling once allows us to retain that information. So we have the same amount of information in the end. Like I say, there's some fairly deep theory that comes from the fact that our NMR signals don't exist before the pulse happened at time zero that explains that. But again, we can sort of play around with our interface and actually look at that and explore those factors. Before I move on to real data, I just want to point out that if you go to the scripts menu, there is a load operations and save operations. So I can save all these operations out to a list. I won't do it here, and then I can reload them. So again, for teaching, you can hand out to students and stuff a list of operations, have them try to do something, and then be able to load that list in and get exactly where you want to be. But let's move on to real data. So let's go to the File menu, open FID, and navigate to Summer Workshop, Johnson. And let's go into the Ubiquitin Relaxation folder. And experiment number 1, this is Brooker data. It's got the traditional Brooker numbers. Find the SER file. So this works on Brooker data, works on variant adjuvant data. You basically just have to go in. If it was variant adjuvant data, you would find the FID file. If this is Brooker data, you find the FID if it's 1D, or the SER if it's 2D. And let's click open. I'll turn off my complex. So now we have the first FID of an HSQC on the good old Ubiquitin. So we can build up our script exactly the same way we did before. I'll show you much faster ways to do it, but you can imagine, again, that we want to add some appetization, sign bell appetization. We want to add zero fill. We want to add a Fourier transform. And now I'm going to hit this auto scale button. And so, boom, there we have it. So every time we add an operation here, it's going to update this display. So again, we can play around things like our sign bell and look visually. This data, for some reason, actually has quite a large water signal in it. So let's think about dealing with that. Time domain solvent, we can add time domain solvent suppression, which basically is going to fit in a polynomial to the FID. Again, it's got various parameters, and we can play around. The smaller I make this window size, the more effective the suppression is. So the wider a window it's suppressing over, but you have the risk that as you get too small, you're actually approaching your real signal. So you have to be careful with that. If I make this narrow, it makes it a little easier to show that I can actually slide around the position of this. So you can see subtly there that I'm suppressing peaks at various positions throughout. So if you want to suppress a signal that's not exactly at the center of the spectrum, you can go in and put it anywhere you want.
Hey, Bruce?
Yes.
Sorry. So in real life, okay, we when we collect data, everybody, we put considerable effort to make sure that our solvent gets suppressed in the raw data itself. Now, yes, like magic, you're showing that the water just goes away pretty well without affecting the amide protons there. So there must be something got to give, right? So what is the caveat here?
Well, the catch is, as I say, as I get this filter, if you look at this at this peak right here, actually, let's phase this spectrum. I'll come back to phasing so it looks up and come back that. As I get this wider, you'll see the intensity of that peak is going to start going down. So there's a limit depending on how close your peaks are to the water, how broad a region you can suppress. This fortunately doesn't have ubiquity, doesn't have a peak too close to the water. This water is actually pretty bad in this spectrum, so it really is useful to get pretty close, or get pretty small in the window size. But the problem is I'm increasing the window basically over which I'm suppressing signals, and as they get too wide, I will suppress the intensities of my real peaks.
Okay.
And sometimes it's a trade-off, if you're not doing an experiment where you really quantitatively care about the peaks, maybe it's more important to actually suppress the artifacts that come from the water than it is. So it's,
right.
Again, the nice thing is you can actually, easily play around and look and see what's happening. Okay, so we've suppressed the water signal. I kind of quickly did this phasing, so let's redo that again. If I click on this phasing button, I can come in here. Now I got two sliders, and I can interactively adjust the phase. If we needed to do a 0 and first order phase correction, I can put, let's actually auto scale this up. I can put the crosshair on top of the peak there. I can set the pivot there, and now I can adjust the first order phase correction, and the phase at the pivot position won't change, but the phase across, so we have a linear increase in phase across the spectrum. It doesn't need much in this spectrum, so we don't really need to do much of that. Okay, so one more thing, and like I say, we can do all this, we'll do this more quickly in a minute, but when we collect, say, 2D data, we typically collect, for every time increment, we collect 2 rows of data, and this little buttons here, so I'm showing what I'm calling the R, the real, and now I'm showing the imaginary, the second row. If I toggle between those, you can see that those signals are actually quite similar in each one. If I was doing the traditional simplest method, we would actually see signal in the first row and no signal in the second row, because it would be 90 degrees out of phase. The fact that I see significant signal in both of these means that this was collected with a method that has one of several names: echo, anti-echo, preservation of equivalent pathways. It's a way to maintain more signal through the pathway and of data collection, and one thing that was pioneered by Mark Rance. And if you saw the homepage of nmrbox, like me, you may have been very surprised to realize that we lost Mark Rance about a week ago. So when you insert this command, I think we owe a lot of this to him. So if we have to now go to the FID, we're going to insert a time domain combination command. The default is hyper complex data, so I'm going to change this and try a couple options. Echo, anti-echo, that doesn't look so good. Echo, anti-echo, reverse. So now if I look at real and imaginary, the first and second rows, really I see all my signals in the first row and little signal in the second row. And again, if I disable that, you can see basically what's happening is the signal intensity is doubling, because we're taking the signal from the first row and adding to the second row. And that's doubling the signal intensity. We're actually we're increasing the noise by the square root of 2, so we're effectively getting a root 2 increase in signal. Depending on how the data was collected, you might find that sometimes the first row is all positive and the second row is all negative, in which case you'd use this other choice here. So you can experiment and play around with that. I will just mention that there is, and we'll come back and try this later, this auto-generate script will actually look at the Brooker parameters and actually insert all this stuff for you. Won't do the time domain suppression, but it'll figure out that we needed to do echo, anti-echo processing. But I wanted to walk you through this manually. Okay, so that's the first dimension. Let's go on to the second dimension, D2. So now we're actually seeing what is actually kind of an FID collected in the indirect dimension, if you could actually do that. And just to save time, I'm going to insert, rather than individual operations, I'm going to insert some common. So I'm going to insert a sine bell, a zero fill, and FT. And then boom, let's just hit the process button, and we've processed our data. So if you're used to looking at HSQCs of proteins, this will look a little bit funny. It looks actually upside down. These are side chain protons. They ought to be up here. We can insert a reverse operation, or we can negate imaginary values in the second FT, hit process, and now it's reversed the other way. Again, if we did the auto generate, it would have figured out to do that for us automatically, but I wanted to walk you through this manually. When we're doing this processing, there's a selector here, FID and data set. I'm going to go back to dimension 1. If I go to FID, I'm actually seeing the first row with these operations applied. If I go to data set, I'm seeing the full process data set. So let's do one more thing, which I was going to extract a certain region, but some of you may have noticed that the referencing looks kind of crazy here. Water is not at -2 ppm. So let's go to parameters. Talk a little bit here about referencing. When we process this, this is the name of the pull sequence. And so by default, the processed file is going to get that name, but we could have typed in hsqc.nv or hsqc. By default, I process into nmrview.nv format, but if heaven forbid you're a Sparky user, just change this to UCSF and you'll get a UCSF file. Spectrometer frequency and sweep width, instead of actually having to put in the exact numbers, we put in symbols from the Bruker parameter. So SFO1 tells us to get that parameter for the spectrometer frequency out of the ACQU and ACQU2S files, get the sweep width. The advantage of doing this is that once we have a processing script, we could go apply it to a data set from another spectrometer that was at a different frequency, and it would figure out that automatically. So the reference I don't always get, and I need to work on this to get it more correctly from the Bruker parameters, but even then, you're not necessarily going to get the correct value, so it's often good to set in something explicit. So if I click in this menu, I can say that the ppm at the center is, for example, at H2O. Not, ideally we would have DSS in our sample and figure out exactly what 0 ppm was, and we could do that, set the mouse on the correct position. We can figure out exactly, there's a way to type in an exact frequencies here and say that a certain chemical shift is at a certain frequency. Here, what many of us do is just to say it's at water. I look at the temperature of the sample and figure out the chemical shift of water. You can explicitly see that if I do ppm at center and say water ppm, you can see that what I'm actually going to be calculating is 4.736. I like to actually use the H2O because, again, if I use this script on another data set collected at a different temperature, it will get it correctly. So you see, as I put that in, the referencing is now updated. So in fact, this water is around 4.8, 4.7 ppm. The other thing I want to do is set up a region. There's nothing interesting over on this side, so why carry that along? I put up my crosshairs. I'm going to say set the black crosshair at 10.5 and set the red crosshair at 5.0. Right click and say add extract region, and that's inserted a command to extract between these data points. So let's just hit process again and boom. So there we have now nice processed spectrum. If we didn't get the phasing right, we can come in here, turn on slices, look at a slice through the spectrum. If the phaser is off, I'm going to get actually a slice in both X and Y axis. As soon as I turn phasing on, then I'm going to get, if I'm at dimension 1, I'm going to get a horizontal crosshair, and I can go in and adjust the phasing a little bit. As soon as I let go of the phase slider, it's going to update the phase operation, and then basically I'm going to reprocess with those phases. we can do the same thing we did before of setting a pivot at a certain place and setting 0 order on one peak, set pivot, and then go over to a peak on the other side of the spectrum and set the first order phase. Like that. If I want to phase in the indirect dimension, I can just change this from dimension 1 to dimension 2. So I'm seeing the operations for that dimension, and now I'm getting the slider vertically, and I can adjust the phasing there. And again, reprocess. It is possible to calculate all this automatically. It's going to be a little tricky on individual rows to calculate phasing, but we have this option D all. So these are going to be operations that actually apply to the entire data set. So I'm going to come down here to data set and insert a data set phasing operation. I can phase the first dimension, the second dimension, however many there are. If I set it at 0, then it's going to phase both the first and second dimension. So now if I process, that processing looks basically the same because my phases were pretty close to start with. But if I go back to dimension 1 and let's just disable this phase command here and click process, basically it looks pretty good because now the phasing is entirely automatically done by that dephase operation at the end.
Hey, Bruce, I think you got a hand up.
I got a hand up. Okay, I'm sorry, I don't see these things, but go ahead, whoever's, there we
Hey,
are,
Bruce,
Doug.
it's Doug.
Yeah.
It's a really basic question. When you do the slices, can you move
Yeah.
the location of where the slice is located on the window?
Yeah. Let's do that. So let's turn off phasing so we get both of them. So we haven't shown you this whole, you have a lot of things we haven't seen yet. Attributes tab. Again, a little aside for people that are nmrvj users, everything is really, all the GUI's rewritten from scratch here, but I've tried to make things very familiar to nmrvj users. So the spectrum attributes is similar but not the same. So it has a tab for slices. And this offset, so the vertical and horizontal, so I can position where that is, where that one is. Another option, if I click this data set, the tracking button, then the position actually is exactly where the mouse is. So, and that could be useful if I'm actually zooming in on a peak and I want to see the slices right at that peak. It's actually possible to turn on a second slice, so I can actually do slices and have a slice. Let's go back to the full spectrum. So I can have a black slice, and with the red crosshair, I can actually have other slices. I can change the colors of those and then be able to see multiple slices. By default, the slice gets the color of the data set, which is handy if you actually have an overlay of multiple data sets, then you can see the slice for each data set. Or you can actually individually change the color of the slices if you want. So that useful?
Yes, thanks.
Answer that. Okay, turn off slices. Okay, so we've got this processed. Let's do one more thing because I can see a little bit of baseline stuff here. So let's talk a little bit about baseline correction. It can be handy to go in after we've done all the processing. We have D1, D2 are the main processing, and then P1, P2 are post-processing. So they're going to be a list of processing operations that happen after all the previous processing has happened. So let's insert a baseline correction. So baseline, a little different than some people. I actually divide baseline into two things. One, defining what regions are baseline, and you can insert a regions command, and you can actually, if I was back in FID mode there, I can actually come up and put crosshairs up and actually insert baseline region this way and add that in and find regions of baseline across the spectrum. What I'm going to do here is actually use an auto regions command. So insert an auto regions command. And then once it's found regions, what do we do with those? I'm going to insert my preferred baseline correction. There's a baseline polynomial of different orders, BC Wit, the so-called Whittaker perfect smoother, and hit process, and you can see those ridges at the edge of the spectrum are gone. And if I zoom in, you can see now we mostly have random noise without any real streaks through the spectrum. So I haven't talked about scripts other than our very first thing we did was process the data with a script. So if I go to the scripts tab, every time we change an operation and then go to the scripts tab, it's basically updating the script. And for NMR pipe users, you can think of this as your pipe shell script. In this case, it's a Python script. And I have to be careful when I say Python. You cannot run this script just with Python. You have to run it within nmrfx or from the nmrfx command line command, because all these operations require code that is built into nmrfx. It's not in generic Python. But you can do things like all the standard Python flow control. If you want to have, if the spectrum is this way, do this. If the spectrum is that way, do that. If you want to loop over multiple spectrum and process them, you have all the features of Python to be able to do that. So we have at the top just some housekeeping stuff, importing some Python tools that I use. I look at how many processors your computer has and basically auto parallelize. So these guys have a lot of CPUs, cores in them. So it decided that it could use 20. And so it's going to parallelize this processing. A command to open the FID, a command to create the data set, some things that go along with referencing, some kind of lower level fancier things sometimes. Here's the spectrometer frequency sweep with referencing. I should say, I didn't talk about referencing for the second dimension. If you get the first dimension referenced correctly, and it's a proton dimension, then all you have to do is put in N or C, if that's the type of dimension they are, and we'll use basically standard IUPAC indirect referencing ratios to calculate the referencing for the other dimensions. Dim1, these are all the operations that are going to apply to dimension 1. The operations apply to dimension 2. Dim with no number in it, these are data set dimensions, so our D phase. And then we come back, we do another dim1 to do the baseline correction. You can handwrite the script. You don't even need to be in the GUI. You can write this by hand and run it. The single most important thing is you have to have a run command at the end, which actually tells it to do something. While I was looking at that, I saw this little auto update button here, just for fun to show you that. If I turn that auto, let's actually turn off just to make it a little faster, this D phase, which does not parallelize properly. If I come to sign bell, turn on auto update, as I slide a slider, it's actually doing the full processing, so I can actually interactively look. So this works on a 2D, maybe a small 3D, you can actually interactively look at how the processing. So if I change the sign bell window, you can see what's happening there. And we can do this because the process is pretty quick. If I get processed, it processes in less than 100 milliseconds. So we can do it pretty quickly. So let's just pause there. I'm going to go on and process a 3D NUS spectrum in a second, but basic processing questions. Anybody wants to throw their hand up? I think we've kind of hit most of the features there.
Hey, Bruce, it's Doug again. I put my hand up.
Yeah.
For the, you said you could script in Python like a for loop and loop over, for example, a series of spectra.
Yep.
Would that require like the proper Python tabbing or?
Oh, absolutely. So it is, when I say Python, technically it is Jython, which is a Java implementation of Python, but it basically is Python 2.7 and works like Python. So yes, so these scripts don't have any indenting. For people that are Python users, they know that Python flow control all relies on things that are indented. So yeah, it has to look like a real Python script.
Hey, Bruce, quickly.
Yeah.
So before we move on to 3D, so in real life, those other nice window functions you showed,
Yeah.
can you give some examples where people use it honestly, like the Blackman?
Yeah.
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 I know it's a digression, but
yeah, I'll just mention them real quickly. So if I go to appetization, let's sort of lock down. And actually, I should say, you know, we have so many things here that even I sometimes forget what they all are. They're if you go to the nmrfx homepage, and you can always go there if you go to help and say nmrfx website, that'll take you to the website. If you go to analyst and click documentation, then if you on the documentation of the processor, you can get basically processing documentation and proc commands. So all the processing commands are listed here. Oops, sorry, those are special ones. Operations. Where the heck am I going? I'm having a little trouble with my mouse here. Processing buoy operations. There, yeah, proc commands. So everything's documented here. We've actually, to kind of force us to actually write documentation, actually the program won't actually build the documentation for the operations come out of the actual low-level Python code, and that won't actually build unless you actually have everything properly documented in there to some extent. But you can also see just operation docs right here inside the program, scroll through. So they're documented there. Let's walk down a few of them. So Blackman and Kaiser, it's actually, can I go back to E1? This may be a little tricky with all these guys. Disable, disable, disable. Okay, so there's our sign bell, probably the most widely used in protein macromolecular NMR. Sign bell squared with some shift. You increase your resolution as you go over this way, but you lose signal to noise. Let's remove sign bell. Add in Blackman. Has a rather similar shape to the sign bell squared. So you can see that that's rather similar. So some of this comes down to just looking at your data and seeing which one looks best. Kaiser actually is similar, and it turns out Kaiser has this beta parameter in it, and depending on what you set beta at, it actually at a certain value of beta, it actually is equivalent to the Blackman window, but it has a little more flexibility. But all of these windows have basically a trade-off. You're affecting two things. One, getting rid of those sync wiggles, and that depends on making the signal go to zero. You're affecting the height of the peak, and you're affecting the width of the peak. And depending on what you're trying to accomplish and what spectrum you're doing, you always have some trade-off amongst those three things. So the Kaiser, as I said, is considered somewhat optimal because its trade-off between suppressing the center signal intensity you're at compared to the ratio of these sync wiggles is optimal compared to other windows.
So when we reconstruct the news data, so is there anything like a bias or preference to one of these, or they all?
That's also a good question, because there is actually different ways you can do the appetization. In fact, I actually have some low-level code that actually can incorporate some of the appetization functions happening inside the NUS processing itself.
One can do a trial and error, but in case if it's already a well-known thing, I just want.
I don't know, and this is this is probably a whole good session with some of the more NUS experts, but all of these functions, as you say, are going to interact with the NUS processing to some extent. And so, but coming up with exactly a theoretical, like I say, Kaiser X has theoretical support for why it is optimal in some ways. Some of the others are more ad hoc. And again, like I say, at least in the 2D spectrum, one thing we try to do is to make it, especially with this interactive auto update, to let you actually really go in and play around, because there's,
sure,
it always comes down to the data set you're looking at. Do you care about retaining quantitative intensities? If you're doing an NOE spectrum, you really care that the intensities are reproducible. If you're trying to resolve closely spaced peaks and you don't care so much about how accurate the intensities are, then a different window is going to be optimal.
Right. Makes sense. Yeah.
So that's kind of a hand waving. You need to think about what you're trying to accomplish and then experiment a bit.
Yeah. Thank you.
Yeah. Okay.
Hey Bruce, can I add a comment / question to that?
Yeah.
So one of the things we spoke about at the workshop 2 weeks ago was the possibility of using synthetic data to generate a calibration curve.
Yes.
So if you were to kind of spike your data set here with a couple peaks with known properties, and then played around with these different apodization functions, you could probably put together a pretty good picture of what kind of
absolutely. And that's a feature that I haven't quite added, but actually the simulate thing that I showed you actually shows you the kind of the low level stuff is there to be able to add signals. And we have actually some other examples where we can generate a simulated HSQC, for example. So that would be a good idea. And as I mentioned, we're adding some of the sort of NUSCON scoring functions in here too. So those things, interactive ability, visualization, ability to add synthetic peaks, I think all together would make a nice tool to play with and address some of these things quantitatively. Yeah. Okay, let's
Oh, you've got one other hand up still, Alex.
Yes, go ahead.
Oh yeah, I think I kind of missed the part maybe where we switched to this 2D display, but maybe it's also my problem here. I feel like I'm getting some kind of exception when I hit the process button.
Ah.
There. I know you probably don't want to troubleshoot my particular setup, but maybe there is like some obvious issue.
One thing I'll tell you, it is certainly possible to, software, even though this is, a fair number of years out now, we keep changing, and I've actually discovered just practicing for this workshop today a number of things to fix. What I will say is, if you see this little green button here below the process button, if that turns red, and you can click on it.
Okay. Oh yeah, right.
And it will pop up actually a thing to get the stack trace. It turns out in the nmrbox environment, it's very hard to resize that window to see the full thing. But you can actually see enough of it that you can actually Control A and Control C to copy and paste that. So
okay,
if you send me that, then I can actually see exactly where in the code it's failing.
Okay.
I should actually, before I go away to the other experiment, I should actually, let's actually restart real quickly. I'm going to go to recent FIDs. Or you could actually just go to open FID and reopen this FID open. What I want to show you is that if I just go to scripts, auto generate, hit process, the phasing's not right, the water suppression's not there, but basically it's processed, it automatically inserted time domain combination in the first dimension and inserted the naked imaginary in the second dimension. So pretty much I've got something that I can look at and see and is more or less processed. I can then go in and just, fine tune the phasing. Whoops.
Oh, I see. It might be just, yeah, it throws an exception there. Okay, it's just me.
So the
issue of my setup.
You inserted something, and I've also inserted something here that's messed this up. My phasing must have been wrong. Anyway, I think, yeah, Oh, there we go. Okay. So, you know, we spent like over an hour walking through building up this script step by step. The point is two things here. One, you can usually get pretty close with auto-generate. And if you have it saved, every time you hit process and it's successful, and it doesn't give you the red thing, if it's green, it will write into the same directory where the FID is, a file process.py. And if you just open that file up, you can start from that file. I almost always, when I actually successfully process something, I'll actually explicitly use the save as, and I will save a file that maybe is called process.works, because then I know I've always got a file I can come back to and got something that I know is going to work. Because every time you change a parameter and hit process, it'll overwrite that process.py. So when I've successfully processed something, I like to save a successful thing under a different name. And then I can always come back to that script. And like I say, you can load that script. If you have another HSQC and you want to process the same way, you can go to open and browse into a different folder and grab a saved script. And we're actually hoping to sort of build up a little bit more of a script library that we can populate and that you can populate yourself.